In this chapter, we will cover elimination reactions of organic chemistry. So, as a brief outline of what will be covered in this chapter is we will look at the general mechanism for elimination reactions. What we will discover is that there are quite a few other mechanisms that are possible to explain elimination reactions. The first one that we'll cover is the bimolecular elimination reaction mechanism. Then we will concentrate on the unimolecular E1 reaction mechanism. We'll follow that with the E1 conjugate base reaction mechanisms. And lastly, we'll look at one that we've seen before, and it's the 1,1 elimination reaction. By the way, this elimination reaction here, and it's also known as an alpha elimination. So let us start. So the general reaction mechanism, or what's needed for a elimination reaction to occur, is that atoms or groups of atoms need to be removed from typically a saturated molecule, such as this. So we have here a hydrogen and X, a potential leaving group. If HX are removed from this molecule, we have an unsaturated functional group. This could be an alkene. Later on we'll see it could even be a carbonyl. But this is the general description of the requirements for an elimination reaction. The mechanisms that we'll cover here will be the concerted, or the E2 mechanism, and we'll look at the E1 mechanism, and then the E1CB. So let us start by looking at the E2 mechanism, or the concerted mechanism, or the 1,2 concerted mechanism. Let's describe first of all why it's called the 1,2 or the beta elimination. So here we have the leaving group bonded to this carbon. We can call that the alpha carbon. The carbon over is the second carbon, so it'd be 1,2 or beta, and the hydrogen that's leaving as a proton is on this carbon. So you can now see why it's called the 1,2 elimination or the beta elimination, because the leaving group and the hydrogen that will be abstracted are on adjacent carbons. For the E2 mechanism, notice here this is the transition state. So what's required is a base abstracting this hydrogen as a proton, leaving these electrons to come in to form a double bond here, and our leaving group leaves, taking the electrons here, and that's why it's X minus. We could put 2 dots here just to indicate that these electrons go with the leaving group. Notice what's formed here is an alkene, an unsaturated functional group. This is the transition state. As you recall, the transition state is a description of the bond making. Here's the bond making, or the bond breakage. Here's the bond breakage, and another bond making process right here, and another bond breakage process right here. So this gives you the transition state in going from this reactant to this product. It's possible to have a 1,3. Now you know why it's called a 1,3, because it's now not on the adjacent carbon, but on the third carbon from the carbon that has the leaving group. So here's a carbon with the leaving group, 1, 2, 3. Here's a hydrogen. That's fairly acidic because it's a benzylic hydrogen, so the base can abstract this hydrogen to create a potential base right here, which can in fact form a bond here to give that as a leaving group. So this would be your transition state here, where this bond is being formed to form the base H+, and we have a new bond that's formed here while the leaving group leaves, and we can again put 2 dots here to indicate that these electrons, or these bonding electrons, are now with our leaving group. So now this is not, notice, this is not an unsaturated compound, but it's a cyclic compound because of the geometry of the leaving group and the hydrogen that was abstracted, a 1,3. As you can imagine, there can be 1,4 depending on the nature of the molecule. Here's another option. This is a 1,4 where we have here an intervening double bond. So let's look at this reaction here. LDA, you will recall LDA is a strong base, lithium diisopropyl amide. It's a strong base. Here's our leaving group here, so it can leave. And here is a hydrogen that's potentially acidic, so the base can abstract this, and that's a leaving group. So let's see how this mechanism is possible to give this as our product. So LDA, a strong base, abstracts this hydrogen as a proton. These electrons swing in. This is a conjugated system now, so these electrons can swing in here, and the OCH3 leaves with its electrons. So again, I should really have here OCH3 with its bonding electrons, and of course a negative charge because it's an anion that's left. So this would be the transition state where a bond is being formed to the base, and of course the electrons come in and our leaving group leaves. So as you can imagine, the other product here is LDA bonded to an H, of course. So that'd be LDA plus, because, well, it's be LDA because LDA is lithium diisopropyl amide, so it would not be neutral, and of course the lithium would form the salt. But the bottom line is that the LDA strong base abstract this proton here, and because this double bond is intervening between these, the leaving group and here, we form this as a possible product. Notice here we have indicated deuterium here. So what I'd like for you guys to really combine your knowledge here is that what would be the isotope effect, or is there an isotope effect on this reaction here? And as you can see here, a CH bond is broken in this step. The question now, is this the RDS for this reaction? If it were the RDS, and we'll find out in a second, then we would see a kinetic isotope effect because a CH bond was broken. Notice also again that we also have here a sp3 carbon, and over here it's an sp2 carbon. So again, there should be a secondary isotope effect here. So again, don't forget to really combine and utilize the knowledge that we've gained throughout this course to assist us understand and solve problems. So here is the energy profile for the reaction for the E2 reaction here. Notice one step, bimolecular, concerted. So the reactants would be the base and the electrophile, or the molecule that has the leaving group, reacts in one step to form a transition state. and then onto products. No intermediates are formed here for the E2 reaction. Let us turn our attention to the geometry requirement. You will remember that for the E2 mechanism, the geometry is a trans requirement because the base abstracts the hydrogen on the adjacent carbon, which is opposite to the leaving group on the next carbon. So here we have a carbon that has the leaving group. On the adjacent carbon has a hydrogen that's trans, but on the adjacent carbon here there's also a hydrogen, but this hydrogen is cis to that leaving group. So in the presence of a base, we would not expect that hydrogen to be abstracted, because the requirement for a E2 elimination is that the leaving group must be trans to the hydrogen that's been abstracted by the base. So therefore, this chlorine and this hydrogen being trans will form a double bond here and not this as the E2 product. So again, look out for the trans elimination for the E2. Let us turn our attention now to the size of the base and the groups that are surrounding the leaving group. As you will recall, a base is required in the single step for the E2 elimination to abstract the hydrogen. So here is a hypothetical molecule, carbon, which has a leaving group here. We have two adjacent carbons bonded to it as shown here. This carbon has 3 hydrogens. This carbon, however, has 1 hydrogen and 2 bulky alkyl groups. Well, at least bulky in terms of they are larger than hydrogen. So if we have a base, it can come in and abstract this hydrogen to form the more stable alkene or the more substituted alkene as shown here. So a small base such as KOH, we'll see examples in a second, will abstract this. However, if we introduce here a bulky base, it cannot gain access to this hydrogen, but it can gain access to the more accessible hydrogens over here because they're small, much smaller, so they are accessible to a bulky base. So this bulky base here will abstract one of these hydrogen as a proton. These electrons will swing in to form the double bond here. So this would be the major alkene, major product. Notice it's not the most stable product, but it's the major product from this type reaction as shown here. So let's see what are some of these bases. So example of a strong bulky base, as we said, it's LDA is an example. Lithium diisopropyl, here's the isopropyl group, 1, 2, 3 isopropyl, and it's 2 isopropyl, so it's diisopropyl amide. So these isopropyl groups here make this LDA a very bulky base. It's also a very strong base because, as you can imagine, the conjugate acid of this base is the amine. So that's a very, very poor acid. So this is a very, very strong base. Another bulky base here is the tert-butoxide. As you can imagine, we have 3 alkyl groups around the basic oxygen here. So that's bulky. Small bases, as you can imagine, is OH. And of course the methoxide. If you get any larger than ethoxide, then that may be bordering on being a bulky base. So for these reactions, if you need a bulky base, LDA is typically used. And if you need a small base, Potassium methoxide is typically used because it's soluble in organics, well, more soluble in organic solvents such as methanol compared to KOH. Let us look at the reaction again, applying what we just learned to using a small base. So here's a small base. Here is the electrophilic carbon with the leaving group here. So in fact, this carbon has a adjacent carbon with a hydrogen, and notice it also has an adjacent carbon here with 3 hydrogens. Because this base is relatively small, it can come in and form the double bond here to give the major product here, which of course is also the most stable product based on substitution of the double bond. So this is a tri-substituted double bond, 1, 2, and 3 alkyl groups that are bonded to the carbons of the double bond, tri-substituted. Remember, the more substitution on the carbons of a double bond makes that alkene more stable compared to another alkene that does not have as many alkyl substitution on the carbons. It's also possible to abstract this hydrogen to form the double bond here. As you can see, here's a transition state, and here is the double bond that's formed, but this is the minor product here if we are using a small base. On the other hand, if we're using a large base such as LDA, it can abstract this hydrogen even though it's very crowded, it's transition state, but that now becomes the minor product. If we use the LDA, it can abstract a hydrogen from this carbon because they are more accessible to a bulky base, forming the double bond here, transition state, and now this would be the major product. Major product here is formed based on the use of a bulky base. Notice again, this is this least stable alkene because it's 1, 2 disubstituted alkene, whereas this is a 1, 2, and 3 trisubstituted alkene. So here again, based on the reaction conditions, a bulky base versus a small base can give different products using the E2 mechanism. As a summary, this is a electrophile carbon with a good leaving group. Here are our actual carbons on the adjacent carbon with hydrogen. So we have 2 hydrogens here and here, likewise here and here. Notice there's another carbon here with 3 hydrogens. So these hydrogens are more accessible compared to these hydrogens. I hope you can see that these 2 hydrogens here, or these 2 carbons here, are in fact equivalent, which means that these 2 hydrogens are equivalent to these 2 hydrogens here. So in the presence of a bulky base, the alkene will form here because it will abstract one of these hydrogens because they're more accessible. In the presence of a small base, that small base can abstract this hydrogen or one of these hydrogens to form the more stable alkene. Some terms that you will be you are familiar with based on your previous organic chemistry course. This is called the Zaitsev product, and this is called the Hofmann product, a less substituted alkene, Hofmann, and the more substituted alkene is called the Zaitsev product. So just kind of remember those names as you read through the different literature. Let us now turn our attention to the size of the leaving group. The size of the leaving group. As you can imagine, they're bulky leaving groups and they are small leaving groups. Here's a very bulky leaving group, as you can imagine, in trimethylammonium salt. So it's a good leaving group because when these electrons are taken with the leaving group here, you form here a very stable molecule here, which is a neutral amine. So that's a very good leaving group, but it's bulky, as you can see here, very bulky. This carbon has a leaving group, so here is the beta carbon, here is the beta carbon, and it has a hydrogen and a hydrogen here. A small base can access this hydrogen much better than this hydrogen. So using a small base such as OH will create here the Hofmann product, or the alkene that's less substituted, or the less stable alkene as a product. So here's an example. So we have here KOH reacting with this. Here is the alkene, because it will more than likely abstract one of these hydrogens here, because that's more accessible compared to a hydrogen over here, because there's more crowding on this hydrogen compared to one of these hydrogens here. You may recall that this type of reaction is called the Hofmann elimination, to give here the Hofmann product, or the less stable alkene. Let us turn our attention now to another type of reaction, which is the same but just an intramolecular reaction. So in this type of reaction here, the base is on the same molecule that has the leaving group and the potential hydrogen. This reaction is known as the Cope reaction, or the syn-intramolecular concerted reaction. Syn because it's on the same side here, and intra because it's on the same molecule. Concerted because everything happens in one step. Notice a concerted reaction here is a reaction that occurs in one step, one transition state, no intermediates. So let's look at this. So here is a carbon that has here a nitrogen, potentially good leaving group, but it also has here an oxygen, which is a base. Don't forget that we have pairs of electrons here. So it's basic, so as you can see, it can abstract a hydrogen here on this carbon. This can swing in, and now this leaves. So the base is now the leaving group. So the alkene forms here. As you can tell here, this is the enantiomeric carbon compared to this, where this group is in the back, and this is in the front compared to here. So same type reaction here. So this gives a product. The difference in products here is that notice that this methyl group here and this methyl group here are on the same side. Wedge and wedge, so here they are on the same side. However, here they are on opposite sides, so that's why this is the trans alkene. So again, look out for the stereochemistry. And notice here, this is going to be a syn abstraction because of the geometry of the base and the hydrogen. It forms here a cyclic 5-member cyclic transition state here, as you can imagine. Electrons are formed here, a bond is being formed here in the transition state. It's broken, it's been formed, it's been broken, and that's your transition state. Again, since we have a carbon here, let's go here, carbon here that has hydrogens, it's possible to have an elimination with one of these hydrogens over here. So I've drawn this like this. So this carbon is right here, And of course, I've just shown that this hydrogen can be abstracted, and we have here, as you can see here, the alkene comes in to give this. The base comes in, abstracts this comes in to form the alkene that's formed here. That's a less stable alkene, but a possible product. As you can imagine, this is the minor product, and these are the major product based on the stereochemistry of the reactant. Let us turn our attention now to the E1 mechanism. Elimination unimolecular mechanism here. So in this mechanism, the leaving group leaves to form a carbocation, and we have seen this before when we looked at intermediates. We looked at the carbocation. This is one way of generating carbocations, is by using a good leaving group and in a good solvent, ionizing solvent. This leaving group will leave to form a carbocation. That's an intermediate. That's typically the rate determining step, RDS, the slow step of that reaction. In the presence of a base, it can abstract a hydrogen from either side of this carbocation. So you got to look out for that carefully, because now we have carbons on either side of this carbocation. If there is a hydrogen, the base can abstract it to form an alkene, as shown here. And that's the fast step. So that's the mechanism for the E1 mechanism, for the E1 elimination reaction. And here is the electron profile, the energy profile, I should say, energy profile, pardon me. These are the reactants, and this is the intermediate. So here's the transition state for the formation of the intermediate carbocation. So this represents the bond breakage of the leaving group from the carbon. And of course, this is the second step, the fast step, where the carbocation reacts with the base by abstraction of the hydrogen as a proton in a fast step. Notice a fast step here because the energy of activation is low. The energy of activation here is much higher, so hence this represents here the rate determining step of the reaction. And of course, the final is the elimination products. So don't forget, this represents here the E1 mechanism in which a carbocation is formed. Let us look at a typical reaction, the dehydration of alcohols. So here's an alcohol, as we have discussed earlier, a very poor leaving group. So it will not leave on its own. But in the presence of an acid, a reaction occurs. And we'll see the mechanism shortly. But if it's now converted into a good leaving group in the presence of an acid, I hope you can recognize that now there are the possibilities of double bonds or an alkene formation will be here, here, and here. So here are the two products. Of course, if it's formed here and here, they are equivalent for this reactant molecule here, 1-methyl cyclohexanol. So let's look at the mechanism. So in the mechanism, as I mentioned, this is a poor leaving group. In the presence of an acid, it's protonated to give a very good leaving group. Why is this a good leaving group? Because after taking these bonding electrons here, we have water, which of course, as you can imagine or know, it's a very stable molecule, a weak acid, a very good leaving group. And so as shown here, once this leaves as water, we have here a carbocation. That's the intermediate. This is the rate determining step. Once we have the rate determining step here for the formation of the carbocation, notice again we have 3 carbons that are adjacent to this carbocation right here. So the base water now can abstract this hydrogen to form an alkene. It can abstract this hydrogen to form an alkene, or it can abstract this hydrogen to form this alkene. Of course, this alkene here is the same as that alkene, so we essentially have two products here. This product is a major product because it is the more substituted or highly substituted alkene, the more stable alkene, and hence the major product. Let's look at another example, slightly different. Here's a carbon with the leaving group, poor leaving group, but in the presence of an acid, it's converted to a good leaving group. So we have the possibility here of additional products. A double bond here, a double bond here, and a double bond here, as we've seen here. So as you can imagine, this would be the major product because it's a tetra substituted alkene. Why tetra? One, here's a carbon after double bond, here's a carbon after double bond. That carbon has 1,2 substitution, this carbon has 1,2 substitution, so it's a tetra substituted. Where this, as expected, would it be the minor product because this carbon here has no substitution, just hydrogen. This carbon has 1 and 2. It's a di-substituted alkene. Let us look here at unexpected products. So it's possible to get unexpected products for elimination, as shown here. This is the leaving group in acid converted to good leaving group. You would expect the elimination here because there are no hydrogens on this carbon. There are no hydrogens to be abstracted from the base. So the double bond is not expected to be formed here. So this is the expected. But if you did this reaction, you'd actually get this as your product, an unexpected product. A careful examination reveals that it looks as if one of these groups migrated because this carbon now, which has one methyl group, now has 2 methyl groups. And this carbon that has 1, 2, 3 methyl groups now has 1, 2 methyl groups. So be careful to carry out your observations before you start looking at a possible mechanism. Let's look at a possible mechanism. So we have the OH group here, converted to a good leaving group, leaves carbocation. The base abstracts this hydrogen to form the alkene. However, because this is a secondary carbocation, the migration of this methyl group here with its bonding electrons over to here will generate a tertiary carbocation that's left behind. So here's a tertiary carbocation, more stable abstraction of this hydrogen as a proton will give this as the unexpected alkene. So again, you are familiar with the rearrangement of carbocations when we looked at carbocations as intermediates for reactions. So this is a practical example here of rearrangement of carbocations in the formation of products or unexpected products. Here's one that I think we covered earlier called the Pinacol rearrangement. It's a diol here, 1,2 diol. Poor leaving group, but in the presence of an acid, one will be converted to a good leaving group and leaves, and then we can have an abstraction to form an alkene. In this case, we'll notice it's actually a carbonyl that's formed. But let's see how that's formed. So here, poor leaving group, presence of an acid, protonate 1 becomes a good leaving group, carbocation. It's a carbocation. So what happens here now is that this ethyl group here migrates to this carbon to form a carbocation here. Notice this is resonance stabilized. So it's a very stable carbocation, even more stable than your tertiary carbocation, because it's resonance stabilized as shown here. And then abstraction of this hydrogen gives this as your carbon-oxygen double bond. So notice it's not a carbon-carbon double bond this time, but it's a carbon-oxygen double bond, a carbonyl. In this case, it's an aldehyde because this is a hydrogen back here. So again, this is known as the Pinacol rearrangement. We did this when we looked at carbocations earlier. And notice again the migration here, migratory aptitude. This is the ethyl group that migrated, but it could have been another group. So you got to look at the migratory tendency, as we did when we looked at carbocations previously. Let us look at the elimination reaction here, in which we're looking at halogens, or the halide. So let's look at bromine leaving. Rate determining step, carbocation intermediate. Fast step here, alkene is formed based on abstraction of this hydrogen to give the alkyl product here. That's the fast step. What I wanted to point out here though is that this now is the solvent, and it's also the base abstracting this hydrogen to give the alkene. Okay, so what you'll discover here is that there's always the formation of different alkenes here. So the base, the ethanol, the base, can abstract this hydrogen or this hydrogen to form either the Zaitsev product or the Hoffman product, as pointed out. So elimination reaction. However, what I want to point out here is that there's always a competition between substitution and elimination reactions, because the base can also be the nucleophile. Well, the bases are in fact nucleophile. It's just a matter of how strong the base is or how weak the base is, sometimes described as nucleophilicity. So let's look at this. Leaving group. This is ethoxide, strong base, solvent. Notice here we get 93% elimination, high percentage of elimination. The other products are substitution products, because here again this is the base, but it's also a nucleophile, so it can come in after this group leaves to react with the carbocation to form a substitution product. But if the strong base is not used and just a solvent, you can see here the elimination product drops, so we have more substitution products. So again, you can tailor your reaction conditions to get a higher percentage of substitution or a higher percentage of elimination based on the strength of the base or based on the nucleophilicity of the nucleophile if you need a substitution reaction. Okay, let us turn our attention to the other mechanism, the conjugate base, E1 conjugate base. So in this mechanism here, the leaving group does not leave in the first step of the reaction. The base abstracts a hydrogen here to form a conjugate base. So that's the first step. This conjugate base now reacts, well, forms a double bond here, as shown down here, to kick out, so to speak, the leaving group to form the alkene. So this reaction is called the E1 conjugate base because it's involved here with a conjugate base here. Notice I did not put here a rate determining step because that depends on the reaction conditions and the nature of this molecule. If this hydrogen is very acidic, the base and this entire molecule here come together in one step to form the rate determining step. And of course the fast step would be here. If on the other hand this is a the reactive conditions are reversed, so that this is an equilibrium here, and this can become the slow step where this kicks out the leaving group to form that. So that depends on the reaction conditions. So you have to exercise extreme care here to determine the rate determining step. I think this example has one here. So here's an example. Here, as you can imagine, is a carbon. Let's analyze this carefully here. Here is the leaving group right here on the adjacent carbon. So here is a carbon, and here is another carbon. This is our leaving group right here. Here is our hydrogen. Notice this hydrogen here is fairly acidic because in the presence of a base, it can abstract this hydrogen to form this conjugate base, which is resonance stabilized with the Cn and also this group here. So you can draw your different resonance structure to show that this is a B conjugate base, which means that this hydrogen is acidic. Because this equilibrium drives to the right here, we say that, well, so this conjugate base forms, and then in another step this forms the unsaturated product here, and this is our leaving group. Notice again, it's an oxygen with a negative charge, but again it's resonance stabilized with the phenyl ring, so it's not a bad leaving group. So what I did this as shown in the text, because that's deuterium, so they observed here a kinetic isotope effect. So that is indicating to us that in the rate determining step, because you saw a primary kinetic isotope effect here, these two molecules came together, so this is the RDS, and of course this becomes a fast step here. So again, you would have to exercise extreme care by looking at the reaction conditions and the experimental results to determine which step of the E1CB is the rate determining step, because it depends on the nature of the electrophile here and the reaction conditions such as solvents and type base to determine which is the rate determining step for the E1CB. Lastly, let's look at a reaction or elimination that we did before. And this is the 1,1 elimination, where the leaving group and the hydrogen, they are on the same carbon, alpha carbon, or the 1,1 elimination. We saw this when we looked at the generation of the intermediate carbenes. So again, just a review. Here is a carbon that has a good leaving group, and it has an acidic hydrogen. Why is that hydrogen acidic? Because it's bonded to a carbon that's bonded to 3 electronegative atoms, chlorine. So that means that these electrons are mostly on this carbon and not on this hydrogen, making this hydrogen here protic. So a base can come in and abstract this hydrogen to form here the carboanion, and this leaves, and we form the carbene. So again, that's a review. So don't forget to relate the information that we have covered earlier with what we're doing now, which is basically the application of the earlier information. I think this is the last slide. Yes, it is. So again, this is the only lecture we have for elimination reactions. So continue reading in your textbook and working some of those examples, but concentrate on essentially what's presented in the PowerPoints here, because I know there's a lot in the text, but you should still understand the material in the text as you study. So continue to study hard. The next lecture will be on pericyclic reactions. That will be our last for the semester, but I will give more information in my communication. Okay, so continue to study hard. Okay, bye.